We're now back to section 5.4. We've learned the shortcut form to find an antiderivative, and now we are going to be looking at the fundamental theorem of calculus today, so we no longer have to approximate areas under a curve using rectangles and trapezoids. We're going to be able to find the exact area under the curve using the fundamental theorem of calculus. Starting off, Nadine is training for her figure skating competition. Her velocity is given by v of t equals negative x squared plus 6x plus 1 for t in the interval between 0 and 5, where v of t is measured in meters per second and t is measured in seconds. Pause the video, please, if you would. If you can just, in your own words, describe Nadine's velocity over the 5-second interval. So v of t is our velocity function, and if we look at that equation, we notice that it's a parabola that opens down. So she starts off, when she starts at time t, times 0, she starts off at 1 meter per second, and then she's getting faster and faster, and when she hits her max speed, she then starts to slow down. So now I'd like you to interpret this integral of 2 to 5 of v of t dt in the context of this problem. What does it mean in the context of this problem? Well, remember, it's an accumulation function. So this is the meters she accumulated between t equals 2 and t equals 5 seconds. So again, remember that that integral from 2 to 5 of v of t is the net distance that she traveled. It's the displacement. It's where is she when she ends up in relation to where she started with. Now I'd like you to, again, pause the video and use your graphing calculator if you have it. Use the Math 9 on your calculator and see what it gives you for that interval. Again, make sure you're plugging in that equation up there. And hopefully when you do that, you're going to get that she traveled 27 meters. Now again, I would like you to pause, think about what we did yesterday, and give a possible solution, possible position function that could represent Nadine's position in meters from one end of the rink at time t. So from what we learned yesterday, we would have a c there, right? But I want you to just guess where her initial position is. So I put that she's at 10. Now I'd like you to find the change in position between t equals 2 and t equals 5 using your equation from question 3. If you have a different value or you want to put in a different value, I would encourage you to try a different value besides 10. Go ahead and find those values. When I do this with my function, I find that s of 2 is 21.3 repeating, and s of 5 is 48.3 repeating. So if I want to know the change in her position, I'm going to take s of 5 minus s of 2, and if I subtract those, I get 27. And how are your answers in questions 2 and 4 related? They are the same. So what does that tell us? That tells us when we found the interval from 2 to 5 of v of t dt, how did we do that? We took s of 5 minus s of 2. At t equals 2, Nadine is 12 meters from the edge of the rink. Where is she at t equals 5? Well, at t equals 2, she's 12 meters from the edge of the rink. And I just found out up here that from the second to the 5th second, she traveled 27 meters. So I can just add that 27 meters on, and I know that she went 39 meters from the edge. Now we need to find Nadine's actual position. Well, if I remember from up here, I found that s of t was negative 1/3 x cubed plus 3x squared plus x plus c, right? I just put that 10 in there just because that's what I wanted to do, but we actually don't know what it is. But we're given this information. At t equals 2, Nadine is 12 meters from the edge. So I can do that. I can plug 12 in for that, and if I plug 2 in for each of my x's, and then I'm going to go ahead and solve this for c. I'm going to get that 12 equals 11.3 repeating plus c. If I subtract that, I get that c is 0.6 repeating, which hopefully you recognize as 2/3. So my position function, I can now go ahead and take what I have up there. Again, 1 negative 1/3 x cubed plus 3x squared plus x plus, now I know that my c is 2/3, and that's my position function. So now the important idea, the integral from a to b of f of x dx, we knew that we could write that as a capital F of x. We know that that means that we're talking about our antiderivative. And normally, as of yesterday, we would put a plus c, but we know how to deal with that. In our notation now, we either put a line or that short little bracket, and we put those limits of integration. And basically what that tells us to do is that we're going to take f of b minus f of a, and that is going to give us the area under our curve. We need to recognize that f of x is the antiderivative of f of x. Big X, or big F, and little f. In other words, big F prime of x equals little f of x. Rearranging what we have above, this is basically kind of the format that we used for number 6 on the first page. Now let's check our understanding. The temperature of water in a tub is given by a strictly increasing twice differentiable function Wt. Selected values of Wt are given in the table below. Evaluate the integral of 0 to 20 of w prime of t dt and interpret your answer in the context of this problem. Well, again, remember that the integral and the derivative undo each other, so basically what I'm finding is w 20 minus w of 0, which is telling me I'm taking 71 minus 55, and I'm getting 16 degrees. In the context of this problem, this is saying that between when the time equals 0 and t equals 20, the temperature of the bath had a net change of 16 degrees. Problem number 2. The graph of g prime of x is given below. If g of negative 2 is negative 11, find g of 4. So this is using our example above. So g of 4 is going to be equal to g of negative 2 plus the change from negative 2 to 4 of g prime of x dx. Again, g of negative 2 is negative 11. And then from negative 2 to positive 2, we have a semicircle. So the area of a semicircle, so it's half of a circle. So first of all, we have half of the circle, and then times pi r squared, and my r is 2. And then I have the triangle. So the area of a triangle is 1/2 base times height. My base is 2, and my height is 2. So when I take care of this, I get negative 11 plus 2 pi plus 2. So my final answer is going to be 2 pi minus 9. Number 3. If g of x is the antiderivative of f of x, and g of 3 equals 5, then g of 8 is going to be what? Well, I have my 5, and then I need to find what's the accumulated change from 3 to 8 of f of x dx. So which one does that match? D. Now using what we did yesterday, being able to find the antiderivative of a function, and what we learned today with the fundamental theorem of calculus, given that we have limits of integration, I would like you to evaluate 4, 5, and 6. So the antiderivative of 3 with respect to t is going to be 3t. Now I'm going to plug in the 3 times 10 minus 3 times 4. 30 minus 12 is 18. Again, this one, the antiderivative of 3t is going to be add 1 to the exponent, so I have t squared and then I'm going to divide by that, so I have 3t over 2, or 3/2 t squared, and again I'm going from 4 to 10, so 3/2 times 10 squared minus 3/2 times 4 squared gives me 150 minus 24, which is 126. And finally, adding 1 to my exponent tells me I'm going to have a t cubed, and then I need to divide by that 3, so 3 divided by 3 is just 1, and again I'm going from 4 to 10. So 10 cubed minus 4 cubed, 1000 minus 64 is 936. Number 7, let f of x equal the integral from pi to x squared of the sine of t dt. Evaluate the integral to find a function. So again, the integral of the sine is the negative cosine of t, and we're going from pi to x squared. So negative cosine of x squared minus the negative cosine of pi. I can evaluate the negative cosine of pi, so this is just going to be the negative cosine of x squared. Cosine of pi is negative 1, so a negative and a negative 1 and another negative 1 gives me negative cosine x squared minus 1 is my function f of x. Now we need to find f prime of x. So the derivative of the negative cosine of x squared. So the derivative of the outside, the derivative of the negative cosine of x squared, is going to be the negative or positive sine of x squared. So that's the derivative of the outside times the derivative of the inside. Remember, that's that x squared, so it's 2x. I'm going to rewrite this as 2x sine of x squared. I'd like you to take a look at this and study this, and how does this extend your understanding of that second, we actually learned it first, but that other fundamental theorem of calculus. So we can still use this when finding the derivative of an accumulation function when the upper bound is not just x, but a function. So if we have the integral from a to some function, we'll call it u of x, of f of t dt. Now remember, if that was just an x and we were finding the derivative with respect to x, if that was just an x, we would just have f of x. But it's not just an x. What did we do up here? We still took the derivative, so we would still have f of u of x, but then we had to multiply it by the derivative of that upper limit function. You now have the basic understanding, knowledge of finding an integral, of finding a definite integral, of finding an area under any curve. I hope you come to class with lots of questions. I'll see you there.